Thanks, Anna, for flattering me again. This is really unrelated to the talk 2 days ago, and it's also much more polished talk because I've given this one for quite a while now. The result is, the paper is at this point almost a year old, and the result like 2 years old. But every once in a while, a little bit, like a little remark comes out. So maybe the last slide will be new to some of you. Otherwise, well, I will try to take a little bit longer on some of the details of particular cases now because I have more time than the usual time. Oh, hi, Sheila. I think your voice, your audio now works, right?
Wait.
Yes. Okay. So the papers on the archive, the slides are on the website. Can you repost the slides in the chat? The link, I mean. Thanks. So let me start with some words that all of you know. A poset is a partially ordered set. We draw these posets by Hasse diagrams. We only care about finite posets here. And we use these notations, this kind of bird eye. This means U is smaller than V and there is nothing in between. And this means U is larger than V and there is nothing in between. Now, here is a construction that's very simple, but we will use it a lot. Given a finite poset P, we define P hat to be the poset P with two extra elements adjoint. An extra element called 0, which is smaller than everything, and an extra element called 1, which is larger than everything. So we just put our poset inside an interval, so to speak. The notion of a linear extension is well known, but just to make the notation concrete, let me say that for me, a linear extension of my poset P is a list that contains every element exactly once. And if Vi is less than Vj, then I less than j. So a smaller element cannot appear further right than a larger element. An order ideal of a poset is a subset that is closed undergoing down. So if you have an element in the order ideal and an element that's smaller, the smaller one must also be in the order ideal. The order ideals are not really a hero of this talk, but they are in a way a motivation for a lot of what follows. So let me talk a little bit about them. And here are a few examples. Every time the poset is everything and the red vertices form an order ideal. So gamma is in there and therefore alpha is also in there because alpha is downwards from gamma. Now, on the set of order ideals, there is a map called classical row motion. And this map has many names. It has appeared in Lie theory. It has appeared, of course, in combinatorics, to some extent in graph theory even. And people have studied it under all of those names with in different guises. So what does that map do? This map takes an order ideal to a new order ideal, which I call R of S. So I call the map R. So what does this map do? First of all, it inverts the colors. So it takes the complement of the order ideal. So the original order ideal was black. Now I take the complement, this is blue. The next step is so this is now an upwards closed set, and I boil it down to its generators. So I only leave the minimal elements. In this case, it means that I only leave those two elements, the blue ones, the ones at the bottom. Next, I turn it back into an order ideal by completing it downwards. So everything down from a blue element will also be covered blue. And that's R of S. So this three-step dance is this is probably the easiest way to define classical row motion. There are others. So you take the complement, you boil it down to the minimal elements, and then you saturate downwards to make it an order ideal. So this map is a permutation of the set of order ideals. You can always revert it. So it has finite order because it's a finite set. But per se, finite order doesn't mean small orders. And often this order is actually pretty large. It's like, think of size of JP factorial. So no surprises there. What's interesting is that for some kinds of poset P, it has a much smaller order than you would expect. Some kind of small power of it is already the identity map. And the best example for this is probably the P by Q rectangle. This is what it looks like. It is a product of a P chain by a Q chain, and this is the case P equals 2 and Q equals 3. So for such a rectangle, the order is very simple. It's P plus Q, which is much smaller than you would expect. So here's an example. This here is an order ideal of the rectangle. So it consists of the red elements, nothing else. You apply row motion once, you apply it again, you apply it again, you apply it again, and you apply it again 5 times in total, and you go back where you started. And that's because 2 plus 3 equals 5. The order is 5. So this is a result that I think is due to Cameron and von der Vlas in the 90s, but other people have restated and reproved it. Other posets for which the order is nice is, for example, include this triangle. And by this triangle, I mean, of course, any triangle of that shape. So this is just the P equals 4 case. And in this case, the order is 2P, but even more surprisingly, after P iterations, the picture just gets reflected in the vertical line. So it's strange because the symmetry is not really built into the definition of this map. And yet, if you do it P times, everything gets swapped, gets flipped across this vertical line. There are more general families of examples, including various ones from Lie theory. It's not surprising that these are like root posets or weight posets of certain representations. It has to do with minuscule weights in general. So there is quite a few more classes of posets for which the order is nice. There is an alternative way to define row motion, which is in a way more manageable, because instead of defining it using 3 like big maps, you define it by a composition of many little maps. And little means very simple. Only one thing can change in a single map. So these maps are called toggles. If P is a poset and V is an element of P, then the V toggle is a map that sends order ideals to order ideals. And what it does is, if the element is not in the order ideal, but you can add it to the order ideal, you add it. If the element is in the order ideal, but can be removed from it, you remove it. And otherwise, you just don't do anything. You just leave it as it is. So in other words, it's toggling the element V if it's possible. And by possible, of course, I mean I want an order ideal, so it better be an order ideal after I do it. If not, I just forget about it. I just undo it. So try to add or remove the element V. And if the result is no longer an order ideal, then you just don't do it. This is a very general paradigm. You can do this with any kinds of objects. Try to make a change, and if the change breaks the axioms, then don't make the change. And people around Jessica Stryker have actually studied other classes of such toggles, but there is much more to study. You can play this game with metroids and with whatnot. Anyway, so how do you get this row motion map out of these little toggles? Well, you just compose them. Only problem is you have to specify the order in which you compose them. And but you don't have to specify it completely. It's enough to say the order is down from the top. So formally speaking, you pick a linear extension, and then you start by toggling the topmost element or the rightmost element, and then moving left. And if you have several linear extensions, it doesn't matter which one you take, the result will be the same. This is a nice little exercise if you haven't seen it already. So for example, let's play this game with this little order ideal, toggle 2, 2, but this toggle doesn't change anything, because if you added 2, 2, then the result would not be downwards closed. So you cannot add it. So you don't do anything. Next, let's toggle 1, 2. And 1, 2 can be added because it will not break the axiom if you add it. Then toggle 2, 1. Now 2, 1 cannot be added, but it can be removed because it's in the order ideal and it doesn't break the axiom. And finally 1, 1. And this is another case where you cannot toggle it, because if you remove 1, 1, then 1, 2 is ungrounded. So it would break the axiom. So this is the result. You got the same result as you would have gotten with the original definition, but now you did it by a sequence of 4 easy steps. So all of this is pretty well known. People still come up with new results about row motion, but most of these results are about taking more complicated classes of posets. I think there is some work forthcoming by, I think, Ben Adambaum at least, but probably a few others. There are various classes of posets, not just least theoretic ones for which this map has nice properties. So this is not as easy as it sounds, because depending on the posets, it can be pretty complicated. But this goal of this talk goes in a different direction. We will actually stick with rectangle-shaped posets. In a way, the nicest picture ever, the nicest kind of poset. But we will generalize row motion, and we will generalize it several levels up. We will define non-commutative birational row motion. So this came out originally in work by Einstein and Prop, and then it was studied by Tom Robbie and myself. A few other people have joined. The ideas go back to Kirillov and Berenstein, and maybe to some extent even to Schützenberger. And the main topic for today is to extend this P plus Q order theorem to this general level. And I will ask some questions which are still open. So non-commutative birational row motion doesn't work with order ideals. It works with what we call labelings. So you start with a ring, which might not even be commutative. It can be any ring. And the K labeling of our poset is a map from P hat to K. So what you think about it as follows. Basically, for every element of the poset, and also for this new extra elements 0 and 1, which give you P hat, you define an element of your ring. You call it the label as this element. And you draw it accordingly. So you draw the Hasse diagram, and then instead of putting down the name of the element, you just put down the label. So this is a Q labeling of a rectangle because it's a labeling by rational numbers. Now, this is in a way the most complicated things that you actually have to understand in this talk. So this is a definition of a birational V toggle. What does it do? So it is a partial map that sends labelings to labelings. A partial map because you have to divide, and when you divide by something, there is always a chance that the denominator is 0, so you cannot divide. And because we are working in an arbitrary ring, that is even worse than it could be, because the denominator, even if the denominator is not 0, there is no guarantee that you can divide by it. So we just say, well, we'll try to divide, and if we cannot, then it's undefined. So it will only be a partial map. And I will use this notation M bar for the inverse of M. I don't want to actually use any division signs because the ring isn't commutative. So the question is always, what is A divided by B? Is it A times B inverse, or is it B inverse times A? So I don't want to make this, I don't want to choose, I just use inverses instead of division. Now, so TV is this birational V toggle. What does it actually do? It transforms a labeling F to a new labeling TVF. This new labeling, what are its labels? Well, at any vertex other than V, so at any element other than V, the label is not changed. So if W is not V, then TVF of W is just F of W. It's the old label. The only label that changes is the label at V. So this is why we call it as V toggle. It's just changing a single label. What happens at V is the following. The label at V gets inverted. So you take the reciprocal. Then you multiply it from the left by the sum of all the labels directly under it. And by directly under, I mean just a little bit lower. So it has to be under V, but there has to be nothing in between. You don't go several layers deeper. You just go one layer down. And on the right, you multiply it by the harmonic sum of the labels above it, again, directly above it. So what is a harmonic sum? A harmonic, that's just a quick way to say 1 over A plus 1 over B plus ... So the reciprocal of the sum of the reciprocals. And of course, I just spell it out here. Again, this is a partial map. And if any of the inverses doesn't exist, it's just undefined. So that's fine. So one possible value is undefined. And just to reiterate, only one label gets changed, only the label at V. If the ring is commutative, then doing this toggle twice gets you back where you started. In that case, it really deserves the name toggle. In general, it does not, because you have this order question, but still it's you can call it a toggle, because what else do we want to call it? Now we define non-commutative birational rowmotion to be the composition of all these toggles. Again, composing them from top to bottom, so composing them along a linear extension. And this is independent of the linear extension you choose, because if two vertices are, so if two elements of the poset are incomparable, then their toggles commute. And you can get from one linear extension to any other by just repeatedly swapping adjacent elements that commute, that are incomparable. So let's do an example. Here is an arbitrary labeling of a 2x2 rectangle. Like everything is a different value. You cannot get more arbitrary. Now let's apply this rowmotion map to it. So you have to toggle from top to bottom according to a linear extension. So let's do it this way. First toggle this, then toggle this, then toggle this, then toggle this. Note that those extra vertices cannot be toggled and should not be toggled. They're just there to they're only readable, they're not writable. Those labels A and B will never change. Okay, let's start toggling. Let's first toggle this value. This value gets inverted. Then it gets multiplied with the sum of the two values down from it, x and y, so x plus y. And then it gets multiplied with the harmonic sum of the only value above it, which is b. So formally speaking, this is b inverse, but that's just b. All right, now let's toggle this, the y. Sorry, let's toggle x. I'm a bit confused myself. I think I got it. Yeah. I read things in the wrong order. So let's toggle the x. Now, this looks complicated, but it's very simple because there's only one value below and only one value above. So you invert x, you multiply it with the value above, and you multiply it with the value below. The only problem is that the value above is now complicated. So you have to, this stuff just gets copy pasted to here. Then you do the same with this here. So you toggle that one as well. And finally, you have to toggle this one. And this is annoying because now you have two values above and both of them are complicated. So you get this. Now, this looks ugly. Fortunately, it simplifies. You can actually see why it simplifies because there's lots of equal things here. You can kind of factor them out. But then you have to think a little bit more about the sum of, okay, it does simplify pretty nicely. So what is the connection between this birational rowmotion and good old rowmotion of order ideals? Well, in a nutshell, classical rowmotion is birational rowmotion if the ring is the so-called tropical semi-ring. Now, of course, a semi-ring is not a ring. So this is a little bit more general than what I've said. But basically, if you take the tropical semi-ring, so it's a set of all integers where instead of addition, you use maximum, and instead of multiplication, you use normal addition, then you get what is called a semi-ring or even a semi-field. And then to an order ideal of your poset, you can assign a labeling where every element in the order ideal gets a 0 assigned to it, and every element not in the order ideal gets a 1 assigned to it. And this, so T-lab, I call this. And this T-lab is an encoding of order ideal as labelings, and this is injective. So instead of working with order ideals, you can work with labelings over trop Z, this tropical semi-ring. And now it's not hard to see at all that if you look at this definition here of the toggle, what it does is really what the old fashion toggle does. If V is in the order ideal and can be removed, then you remove it. If it's not in the order ideal and can be added, then you add it. Otherwise, you just leave it as it was. Of course, the sum becomes maximum, the harmonic sum becomes minimum, and reciprocal becomes subtraction. Okay, and so row motion becomes birational row motion becomes classical row motion, and anything we prove about birational row motion will then apply to classical row motion, provided that it's true over semirings. And even if you don't like semirings, you can get by using rational numbers, but in that case you have to take a limit. So it's going to be a limiting case, not a particular case. Now, what can we say about birational row motion? It's been 9 years now since our paper came out about the commutative case in 2014, and that paper proved a few fundamental results. But since then, much more has been done. But let me quickly say a few things. So if P is a rectangle, then the order is still P plus Q, the same as for combinatorial. So the map has gotten a lot more general, but this order has not become more complicated. If P is a certain triangle, you get the 2P order. If P is another kind of triangle, again, you get the 2P order. And moreover, if you do it P times, everything gets flipped in the vertical line. So again, the same symmetry comes out. There is a more general result by Soichi Okada about minuscule posets of Lie algebras. And there is also results about certain forests. So a forest is a poset where you just say the children of a node are bigger than the node. And if the forest is graded, so if every maximal chain has the same length, then you get an explicit order for R. However, these nice situations are in a way exceptional, not because there is no others, but because in general, the order is not nice at all. In the classical case, at least the order was finite because it was a finite set. In the commutative ring case, the order is not finite. Here are two very simple posets with infinite order R. And if K is not commutative, things get even worse. This is one of the simplest posets whatsoever, this claw. If K is commutative, the order of R is 6. If K is not commutative, there is no finite order. As there is not even some kind of approximate finite order. It's really complicated. Things can just stop holding for no obvious reason. However, what happens with the really nicest of all cases, the rectangle? So let me introduce some notations. P and Q are going to be the side lengths of the rectangle, by which I really mean the number of vertices on each side. And the rectangle is then the P chain times the Q chain as a poset, entry-wise order. So this is a 3x4 rectangle. Let F be a K labeling, and let A and B be the labels at the very bottom and at the very top. So these are the labels that never change if you do row motion. Now, we claim that if you apply birational row motion over a non-commutative ring now, P plus Q times, then you get your original labels back, but not immediately. Instead, you get them back, but they're trailed on the left and on the right by certain constant terms. A, B inverse on the left, A inverse B on the right. Notice that this is not a conjugate. This is a kind of twist. So, of course, I have to assume that this is well-defined. If you get a division by zero problem, any variance in this, then of course it's not defined. I'm not claiming that you will never have to divide by zero, but if you can make all those divisions, then it's true. And another claim is that, so this will require a little bit more explanation. So this is saying that the labels come back after P plus Q iterations of R. And this is claiming actually they come back a bit earlier even, but they don't come back directly. Instead, their inverses come back. So for every label you see, eventually we'll see its inverse as well, but bordered by A and B. So they conjectured these two results back in 2015 based on the commutative case and just a bunch of computations in Sage. We used matrix rings. So those conjectures were not really well-founded. But back in 2021 and 2022, we were able to prove them. Let me first show you what these conjectures say. This is again the two.
I have a question. Mm-hmm. In your previous page, and if you choose the rectangle to be a square, P and Q the same, is there any simplicity there?
Oof. I don't think so. I mean, you will see the next example where P and Q are 2. So here is the example. This is the rectangle, and this is the 0 and 1, well, the 1 and 0. So here is the original labeling that we start with. Here is the labeling after one row motion. This, I think, you've seen now. Now let's do another row motion. Another row motion. As you see, the terms get big, so I had to skip one. And another row motion. This is what you get after 4 row motions. However, this wild thing actually simplifies, and it simplifies a lot. It simplifies to y. And the thing on the left simplifies to x. So surprisingly, after the entry, after the labels have been getting more and more complicated, in the last step, they again became pretty simple. After 4 row motions, they're just the original labels w, x, y, and z, except with some extra factors thrown in. But the factors are predictable. It's always a b bar on the left and a bar b on the right. This is what the periodicity says for p equals q equals 2. Now about the reciprocity. Here is again the orbit, and this time I've simplified everything as far as possible. By the way, simplifying a rational expression in non-commutative variables is not an easy thing. Technically, there are algorithms to do this. Practically, I don't know if any computer algebra system has them implemented. It's not like Euclidean algorithm or like clearing denominators or whatever. The things that you can do with commutative variables are making the theory very simple. Here you cannot. All right, so here is the orbit. Now look closely at the colors. This green X corresponds to this green X bar. This red Y has a red Y bar here. This W bar, D, Z bar. So every label on at the onset has a mirror image somewhere in the orbit. And this mirror image is its inverse, again, bordered by NB. And there are some more reciprocities here because, of course, you can apply it to the next one as well. Yes, so here are a few other mirrors. So this one gets repeated here with an inverse. This one reappears here, and so on. So how do we prove such a thing? Well, 9 years ago, we proved the results for commutative K using a strategy that, in a way, is not that new. Basically, Volkov proved the logic of periodicity in a very similar way. First of all, it's enough to consider a field because what we're doing is polynomial identities. And then we construct a certain map, which we call the Grassmannian parameterization, GRASP. So it takes a P by P plus Q matrix to a labeling of the rectangle. And explicitly, the labels of the labeling are going to be certain quotients of minors of the matrix. I will not go into the details. The only thing I want to say about this map is that this map behaves nicely with respect to row motion. So to apply row motion to the labeling is tantamount to rotating the matrix. And because rotating a matrix P plus Q times gives you back the original matrix, it's just a cyclic rotation, the same applies to birational row motion, at least if you can prove that this map is more or less surjective. So a lot of technicalities I have swept under the rug, but otherwise, this is a typical case of like using a parameterization to make the map simpler. Reciprocity also gets proved this way. Now, unfortunately, it looks like you should be able to generalize this to non-commutative rings K, because there is a notion of non-commutative determinants. And on the level of those determinants, the map worked. Unfortunately, it's no longer clear why it's almost surjective. It's not even clear what this word means, almost surjective. It's also not true that if you prove something for a skew field, you also know that it automatically holds for rings. Simple example is x times yx inverse times y is 1 for any skew field, but not for any ring. So this approach, even if it worked for skew fields, it would not generalize to rings. Well, at this point, I have no hope in this approach anymore. I think it's a dead end. Maybe somebody can make it work. There was another approach by Greg Musiker and Tom Robbie. This one was much more explicit. It relied on an explicit formula for the label at a given vertex after a given number of row motions. This formula is pretty complicated. This is a sum over families of non-intersecting lattice pairs in a certain lattice. So I will not go into the details. We did not end up using this approach, but we got some inspiration from it. Unfortunately, with non-commutative rings, this too doesn't look very promising. The problem is you don't know in what order to multiply things if we have different lattice pairs. So how can we prove things then? We're out of luck in terms of theory. None of the theories work. So at some point, we got desperate and started playing around with the definitions. So here is a bunch of notations. Because we only care about rectangles, we just fix the rectangle, we fix P and Q, we call the labels at the very top and bottom B and A, and we write XL for the label at X after L row motions. So X0 is the label at the beginning. And then after one row motion, you get X1 and so on. This is a formula that is basically the definition of birational row motion restated. Now, in terms of our new notations, it takes a simpler form. So V1, that's the label at V after a single row motion, is the sum of the labels below V times the reciprocal of the label at V times the harmonic sums of the labels above V. And the subscripts are because these labels are after the row motion, and these are labels before the row motion. So you can think of the subscript as a time variable. If you think of this whole thing as a dynamical system, this is basically the T. Time 1, time 0, time 0, time 1. So this equation is the recursive transition equation of our system. And of course, because we apply the same map every time, we just keep doing row motion, row motion, row motion every time. This is not specific to 0 and 1. You can have the same formula for L and plus 1. Every step is just row motion. Okay, so this is just notations. Now let's rewrite the claims. This is the periodicity theorem. It says that a label after P plus Q iterations is a label at the start with those constant factors. And this is reciprocity. I will not go into the details here. Okay, yeah, actually, maybe I should go into the details of reciprocity, just say one more thing. I should say that the label at I, j, when this label comes back as its inverse, it doesn't come back as the vertex I, j. It comes back as the antipode of this vertex. So basically, the vertex gets reflected across the middle of the rectangle. It's a 180-degree rotation. So for example, the label at the bottom comes back at the top, and the label on the left comes back on, the label on the right comes back on the left. So this is why I call it antipodal reciprocity, but at some point we got tired of saying antipodal. And a simple argument convinces you that reciprocity is actually the most important result. because if you can prove that, all you need to prove the other things, the periodicities, you just apply reciprocity twice. Moreover, so here reciprocity is stated for an arbitrary time L, but it's enough to state it for L equals I plus j minus 1. This is basically the first time at which you get reciprocity, because for any later time, this is just the same dynamics. It's just, you just imagine that you start at time 1 instead of time 0. You just shift the time variable. Okay, but still, that's a tall order. How do you prove this? Even for L equals I plus j minus 1, it's not obvious. So we started doing something that was inspired by work by Joseph and by Robbie and by Musiker and Robbie. We started looking at paths. A path in this case is more or less the same as a lattice path. It is a sequence of elements of a poset, including 0 and 1 if necessary, that where at every step you go one level down. So you always go to a neighboring vertex, either down left or down right. So next we define two kinds of, how should I call it? Auxiliary variables, I guess. AVL and nabla, and sorry, I mean, this is not the all quantifier. This is an A that is reversed for obvious reasons. But I'm going to call it all because I don't know how else to call it. Reverse A? Yeah, I don't know. Anyway, so why is it called A? Because look at the letter A. It's like it has an apex at the top and two things at the bottom. So AVL is you take the label at V at time L, and you divide it by the sum of the two labels as the two elements below V. So V divided by P plus Q. Of course, if there are two such labels, sometimes there's only one. In that case, you just take that one. Okay, and what is the other one? Well, the other one is similar, but you go upwards, not downwards. So and it's a little bit more complicated. So if you have the vertex V and right above it you have P and Q, then what you have is V bar, but now on the left you take the harmonic sum of the labels at P and the labels at Q. You can view this again as a kind of division, but it's not immediate division. It's in a way it's the same thing but reciprocal. Okay, and if V is 0 or 1, you just set it to 1. Moreover, you extend the functions to, so this is defined for a single vertex, and now you define them for paths by just taking the same value for each vertex and then multiplying it along the path. And finally, you do this here. So if you fix two vertices U and V in the poset, and vertex always means element of the poset, it's the vertex of the Hasse diagram. So if you pick U and V, then AL U to arrow V is going to be the sum of APL over all paths from U to V, and likewise with the reverted A's. Okay, so now you have, so starting with the labeling, you have defined this kind of additional values. Can you reconstruct the labeling from the additional values? Yes, you can. It's given by these formulas. If you want a label at a given vertex U, what you do is you sum those A products over all paths from U down to 0. So over all possible ways to descend from the point U to the very bottom of the poset, and you multiply it by the constant A. You can also do this with going upwards instead of downwards, but now you have to use the inverted A's and you have to take the inverse. So honestly, this has nothing to do with rectangles. These formulas are very general. They hold for any poset more or less. And the proofs are pretty easy inductions. These formulas have been known for a while. Michael Joseph definitely wrote them up a few years ago. And here are two variants of these formulas. So basically, in terms of lattice paths, So if you look at this poset, to go down to the very bottom, it's basically the same as to go down to 1, 1 to the very bottom of the rectangle, because the last step is in a way uniquely determined. The last step is not very interesting. So instead of going all the way down, you can go down to this here. It's not a big deal. It's just a technical simplification. Okay, what else do we know about this ace and reverse ace? Well, you know this equation. A reverse a at time L plus 1 equals the corresponding normal a at time L. Why? Well, this is really the transition equation of our dynamical system. This is just the definition of birational row motion restated in a fancy language. And because this is true at every vertex, it's also true for every path. Those values for a path P are just the products of the values for every vertex of the path. And therefore, those other values are also equal. So basically, anytime you see a reverse A, you can replace it by a normal A, but you have to decrease the time variable by 1. So not very much has been done yet. However, we are already in a good shape because we can already prove reciprocity in one case. We can prove that the value at the bottom of a rectangle after one iteration of row motion equals the reciprocal of the value at the top of the rectangle after 0 row motions, reciprocal and with A and B. What you do is you apply the two path formulas. Specifically, for this here, you apply the first path formula, and for this you apply the second path formula, and then you recall back by the transition equations that inverse A1 is normal A0. Again, this is not that new. This proves reciprocity for the simplest possible case, where a value comes back after just a single iteration of row motion. Unfortunately, this is obviously the simplest case. It's the only case where you only need to do one iteration. How do you do the rest? So here, an induction argument came in handy. In a way, the rectangle is really nice. The rectangle locally looks like this. If you look at just a single vertex and its neighborhood, you usually have two vertices below it and two vertices above it. Sometimes less, but most of the time it's really four vertices in the neighborhood. Now imagine that you have proved reciprocity for this vertex, for this vertex, for this vertex, and for this vertex. Then I claim that reciprocity also holds for this vertex, for V. Why is that? Well, because there is a certain symmetry in the definition of row motion, so that if you take all those 5 reciprocities, a certain sum of them is going to be clear. So if you have 4 of them, then the 5th one can be basically follows by canceling those 4 from the sum. I'm not going into the details. You can read them up, but it's really a fairly straightforward argument. So you don't need to prove reciprocity for all elements of the poset. It's enough to prove them for a few elements, and then to walk up the poset from those few elements using those steps, where if you have M, S, T, and U, you get to go to V. Now, how many elements is enough? For how many elements do you need to prove reciprocity so that this argument will then get you through the rest of the poset? Well, it turns out that the only elements you need are the ones with j equals 1. So if you look at the rectangle, this is going to be the leftmost side of the rectangle. So basically, you have lost a dimension. You have simplified the problem so that you only need to do it to prove q many instead of pq many equalities. And of course, we have already proved it for the bottommost point, so we need to prove it for the rest of its sides. Let's try the next higher point, 2, 1. So we need to show that the label at 2, 1 after 2 row motions is the reciprocal of the original label at p minus 1, q. Again, with A and B on the left and right. And using the path formulas again, this boils down to this equation. But now this equation is not at all obvious, because of course you know that you can be that inverse A becomes normal A if you go down one time, so 1 second. But here the time coordinate is the same, so it's not a consequence of transition. But that's also nice because it means this equality does no longer have to do anything with row motion, because both sides are defined at the same time. There is no row motion happening between this and this. It's just a single labeling playing the same, like into both sides. So because it's the same time, we just forget about time. So we just look at a snapshot at this time. So we stop writing the subscript 1. So basically, we need to prove that the sum of the A products along all lattice paths from PQ to 1 is the sum of the reverse A products on all lattice paths from P minus Q to 1, 1. And in fact, more generally, if you have this kind of configuration where you have two adjacent points U and U prime on the top right edge, and two adjacent elements D and D prime on the bottom left edge, then the sum of the A products over all lattice paths from U to D is the sum of the all products over all lattice paths from U prime to Z prime. So this is what we need to prove. I call this the conversion lemma because it converts A products into all products. And it's no longer transition because because the time doesn't change anymore. You don't remote anything. You look at a single labeling, but this time you have A on the left and all on the right. Now, so it's not exactly obvious that this should be true, but it's not hard to see that this is actually equivalent to reciprocity at 2,1. So it's certainly this better be true if the conjectures are true. What's even nicer is that this lemma would prove reciprocity not just for 2,1, but for any vertex on the left border, but you have to apply it many times. Basically, you have to apply the path formula, and then you keep moving down using transition conversion in this order. So whenever you have an all product, you use transition to make it into an A product, and then you use conversion to make it again into an all product. And every time you do transition, the time decreases by 1. So eventually you get down to time 0. And that's how you get the reciprocity. Right, so now the hard part is to prove the conversion lemma. Once you prove this conversion lemma, what I told you is more or less the idea of how you derive the claims from it. But how do we prove the conversion lemma? Here is the picture again. So you have to prove that a certain sum over all the red paths is the same. No, it's a different sum over all the blue paths. Well, a reasonable idea for such a thing is you have to interpolate. So you define some kind of mixed red and blue path, and you prove that you can more or less turn the red path into the blue path step by step. And at every step, the sum stays the same. But the intermediate steps are not actually paths. They are what we call path jump paths. Why path jump paths? Because they look like this. They begin as a path, then at some level you have a jump, and then it continues again as a path. So what is a jump? Well, let me explain it formally. So the path part is here and here. The jump part is here. This is a different relation. This is not covered. This is not just going a little bit down. So the jump, you can jump from a point X to a point Y if Y is one step down and any number of steps right of X. So basically, if you're jumping from this point, you can go to its right bottom neighbor, or to this vertex, or to this, or to this, or to this. So basically, any point starting with the right bottom neighbor and going to the right is fair game. And you say that this path jump path P has jump at I, by which we mean that the jump is from the I, is basically instead of its I step, it has a jump. Now, to every pass jump pass P, you assign the product EP. So this is, remember, we want to interpolate between the A product and the reverse A product. So the way to do it is you take the A product until the jump, and you take the all product or the reverse A product after the jump. And in the middle, you just take the single label at the top of the jump and the inverse of the label at the bottom of the jump. And every time you should think that there is a subscript L, because we're working at time L. Now, why is this an interpolation? Well, if you look at this pass jump pass where the jump is the last step, then this is basically a pass, except it's missing the last step. But if the jump is the first step, then it's a pass without the first step. So your left-hand side is the sum of the EPs over all pass jump pass, where the jump is at the last point. And the right-hand side is the same, but where the jump is at the beginning. And now, so you have to prove that the sum where the jump is at the end is the same as the sum where the jump is at the start. And what is really going on here is that you can move the jump one step at a time, and every time the sum will not change. So it's not just this extreme positions of the jump, but for any position of the jump, wherever you want the jump to be, the sum will be the same. And this, once you know that you're proving this is no longer hard to prove. It takes a few pages, but it's in a way clear how to proceed. Yes, so there is a way to rewrite this argument as a matrix product. I don't know to the extent of which it's nice, but I have to skip it anyway because of time. So much for the proof. Of course, you can read up the details. There are some details in the FIPSAC abstract and more details in our paper. And by the way, even so this proof is long, I think it's still simpler than the original proof. And honestly, I think it's simpler than any proof of this result for the commutative case. But in a way, I don't like it. Why not? Well, classical row motion is not row motion for a ring. It's row motion for a semi-ring, a semi-field, in fact, the tropical semi-ring. And that's not a ring. Now, in the commutative case, you don't have to make this distinction because in the commutative case, all such theorems boil down to really equalities between polynomials. You can just write everything as a rational function. You can clear out the denominators by multiplying through, cross-multiplying, and then you get an equation between two polynomials. And these polynomials have positive integer coefficients because there is no subtraction anywhere in the definitions. So if it's true for fields, it's true for semi-rings as well. However, you cannot make this jump in the non-commutative case. In fact, here is a pretty annoying example. This is an identity that is true for any ring. So whenever x and y are two elements of a ring, such that x plus y is invertible, then x times x plus y inverse times y is y times x plus y inverse times x. This is a beautiful little problem in abstract algebra. I mean, I gave it as a homework problem in my algebra class. Actually, it's pretty simple, but the fun thing about it, it's not actually true for semi-rings. It's true for rings. David Speyer found this on mass overflow. So this is an answer to my mass overflow question. So this is what this tells you is that if you prove any theorem like this, like reciprocity, well, these are identities, of course, and these are subtraction-free identities. If you prove them for rings, that doesn't mean that they hold for semi-rings. Even so, there is no subtraction in them. Okay, so if you want to prove them for semi-rings, you have to start from scratch, more or less. Unfortunately, we don't know how to do it at all. What we know, of course, our argument works for j equals 1. So we can prove reciprocity for elements at the left border of the rectangle. However, the argument where using those elements to get to all the other elements, that argument uses subtraction. You have to cancel equal terms from an equation. and that's a subtraction. In a sum-ring, you cannot do this. You cannot, like from A plus B equals A plus C, you cannot get B equals C. We do have some partial results. I think we know this for a 3 by 3 square or for a 2 by Q rectangle, but we don't know anything further. Other open questions have to do with other posets. Again, the next obvious thing to consider are triangles. So for a rectangle, you have P plus Q periodicity. For a triangle, again, you seem to have 2P periodicity, but even better, after P iterations, everything gets flipped across the vertical axis. But the only difference is now you have those constant factors. I mean, you always get those constant factors when you're doing something non-commutative. You shouldn't expect this to be like completely canceling out. We have some kind of very plausible argument for why this is true, but we don't have a proof yet. There are other kinds of triangles. There are trapezoids as well. For all of them, we have conjectures, but we don't really know how to prove those conjectures for now. And as I said, none of this is automatic. This very simple poset does not have periodic behavior for non-commutative rings. Even so, it has nice periodic behavior for commutative rings. So the non-commutative generality does actually make things harder.
So,
okay,
Darij, is this conjecture already true for commutative case?
This one, yes. This is in our 2014 paper in the commutative case.
Yeah.
In the commutative case, of course, A cancels A inverse and B cancels B inverse. But in the non-commutative, they are far away from each other. You cannot just cancel them across the board. Yes, and we suspect that there is more results in the non-commutative case lurking in places where we might not be looking for them, but I'm pretty sure they're around. So I want to thank Anna for the invitation, Tom for being a co-author here, as this has been a great joint project. My best work comes from this project. We have used the hospitality of several places to work on this, and lots of people have contributed some comments and ideas.
Thank you so much. Thank you. So any questions, Darij? I have one. So like so all these if I'm understanding correctly, you're looking at things in the rectangle case, right? But and also like is it like all the posets that you're considering are graded posets? Are they?
Oh, yes. So if the poset is non-graded, we believe that even in the commutative case, we don't get anything useful.
I see.
Yes, so like periodicity in the commutative case seems to require grading. Even so, I don't think we have a proof of this.
I see.
I also had a quick question. Does the fact that you have two predecessors to an element or whatever play a big role? Because I saw that your non-example had 1 going to 3 or something like this.
I mean, certainly intuitively, yes. Intuitively, it seems to be necessary for the non-commutative case to work. But again, we don't really know why. It might just be because we haven't found the right examples.
Well, thank you.
I should also say we have a couple results for general posets. In particular, yes, so we do have one result that doesn't require graded. That's true for any poset. It's saying that a certain quantity is invariant under R. Specifically, this is you take every edge of the Hasse diagram and you divide the thing at the bottom of the edge by the thing at the top. This is an invariant, at least if the values at the very bottom and top are 1. This is not very hard to prove. It just came out of a side application, but otherwise the general poset case is very wild. We don't expect any patterns.
Any other questions for Darij? right? If not, then let's thank the speaker again. Thank you so much.
Thanks,
Thanks,
everyone.
Darij.
Thank you so much. All right. I will see you all next week on Tuesday. That will be our last lecture. All right. Bye. Have a nice weekend,
Bye.
everyone.